today's agenda would be like we would understand why memory is very important for agentic systems. Okay, and then we would go into different types of memory, and then we would also discuss about how do you manage these different types of memory. We will have some hands-on session into how do you implement the basic memory patterns. So I've already shared all the collab files with Misaj. She will be sharing the collab files with you so that we can have hands-on session. So there are around 11 collab files in that folder. So we may not be able to cover all, but I will try to cover as much as possible. So because we need to also keep up on the time. So whatever collab files we are taking up, I will make sure like it is explained properly. Others, maybe you can use it as a reference. You can go through them. So all the theoretical sections anyway we will be covering. So if at all I'm not able to explain any collab files, you can go through them on your own, and feel free to connect with me. I will be sharing my contact details at the end of the slide. So yeah, I think that's it. Yeah, and we will also look into the RAG integration. Yeah, so these are the 4 topics we'll be covering today. So first we'll look into why memory matters in agentic systems. Okay, so first of all, it's very important for us to. Sorry. Hello.
Yeah, ma'am, that was just a glitch.
Okay. So I'm audible, right?
Yes, yes.
Okay. Yeah.
Clearly audible.
Yeah. Okay. So first and foremost, we'll look into why memory is very important for agentic systems. So for us, first of all, it is very important for us to understand the difference between the traditional LLMs and agentic systems. Okay. Once you understand that difference, it is very important. It is very easy to understand why memory is important for agentic systems. So in traditional LLMs, how does it work? You ask a question, you get a response, and you're done. Nothing beyond that. Okay. You ask maybe you ask a question, say like what is the weather today, and then it gives you a response. The weather in your place is so and so, the temperature is so and so, and then you're done. And how much can you ask? As much as it allows you to, and that is what you call as the context window. Every LLM has a context window size, which is how many tokens. In simple terms, you can take tokens as the number of words. So at a time, you can ask only that many number of words to an LLM. Okay, so how much you ask is limited by the context window, and how long can you chat? It is only for a single conversation. You ask a question, you get a response, and does not remember anything beyond that, right? But agentic systems are not designed that way. Agentic systems are systems that can solve complex problems. When you're solving complex problems, you will have multiple steps, and each steps would require certain decisions to be taken. And how does an agentic system make decisions? It will perceive what is around, it will perceive the environment around it, it will learn from it, and then make decisions. Like, how do we as humans make decisions in life? Like, we might have some past experiences. We might be making decisions based on the knowledge that we have gained so far in our life. We might have done some academics, or maybe we have some work experience. So every decision that we make in our life, right, is dependent on our knowledge and past experiences. Similarly, for an agent also, if it has to make decisions, if it has to reason, it needs to learn from it, or it needs to have some external information, right? Now, how do you provide information to an agent? The only way you can provide information to any machine is through memory, right? So you run code in your laptop, right? You need to have RAM, right? You cannot run your code without RAM, right? So for any machines to have knowledge or information, you need to have memory. So memory is what enables agents to reason over time. It is what makes, that is why you say agents are intelligent. Why are agents intelligent? It is able to have this additional memory or external knowledge or past, it is able to remember the past interactions so that it is able to learn from it and make decisions accordingly. Okay, so what do you mean by memory in agents? As I mentioned, agentic systems are usually designed to solve complex problems which involves multiple steps. At each and every step, okay, it might be doing some computation, it might be getting some information, it might be retrieving some relevant information from some external source. So at every stage, it is making some progress. Okay, to to go to the next step, right? So if at all you have to process the next step, it has to know what it has already done, right? So it stores and updates the information at each and every step into a memory so that the next step can refer to that memory and make decisions. And it goes on and on until you have completed the goal or you have completed the task. So what does memory, how does memory benefit agentic systems? It helps systems to plan things. It helps systems to self-correct. That means I have, maybe I have tried this tool, it did not work. Okay, so sometimes you have a particular situation. For that particular situation, agent has tried a tool, it has failed. Okay, maybe it tried to call in API, so it already has a tool, okay, for that particular task. It also has an access to an API, maybe to retrieve information from a website. So multiple times it has tried to retrieve information from the website, it has failed. Now it will learn that, okay, it has already has a tool, let's use the tool, let's not go for the API call. That is self correction. Third would be personalization. So when you I think when you chat in Gemini these days, you might get some personalized responses. Like, for example, say I usually ask for Python code. Okay, so somewhere the agent learns that my preference is Python. Okay, so whenever I try to write a code, by default it gives me a Python code. Okay, probably if I was a Java developer, it would give me a Java code, right? So that is what you call as personalization. Like, it is giving you responses based on your preferences. Okay, so I hope it's clear why we need. So first and foremost, what we are trying to understand is why do we need memory in agents, and what benefit does memory give agents. So um, in nutshell, what you can say is agents require memory to perform multiple steps so that whatever it has done in the previous step, it should be able to remember and plan accordingly, correct accordingly, and also gives you personalized experiences. Okay. Now, so now there are now we'll move into different types of memory. Okay, so you have based on what information we are storing, we have different categories. One is episodic memory. So what is episodic memory? So maybe like if you recollect about your day-to-day routine, maybe you can say you got up at 6 o'clock, and then maybe at 7 you went to the gym, and then maybe 8 o'clock you return from the gym, and then maybe 9 o'clock you went to office or you went to your workplace, wherever. Yeah, and then you had lunch at 1 o'clock. So this is what you call as episodic memory. So whatever, at what this time, this is what happened. So you are remembering events based on the times, right? So that is your episodic memory. So how sharp is your episodic memory, right? Like, if I ask you like what you had for breakfast today, but if I ask you what you had for breakfast 50 days ago, okay, you may not be able to remember. So yeah, so what is now what is semantic memory? Semantic memory would be like you might have.
Excuse me, are you sharing your screen?
You are not able to see the screen?
Your changing screen is not reflecting, ma'am.
Oh, is it? Oh, oh, sorry. Why is it not reflecting?
Ma'am,
Stop
actually,
sharing
the
and you can
screen is
retreat once again.
visible,
Okay, okay.
but the screen is not moving.
Oh, is it? Oh, I didn't know.
Yes, if you have moved the screen, it's not moving. It's actually
I'll just
visible.
present it. I'll just present it again. Sorry, so
Yes,
sorry. Uh,
no problem.
so now are you able to see?
Yeah, it's okay.
Yes,
Yes.
yes, ma'am.
Oh, so you were not able to see it all this while. Oh, no, so
Actually,
sorry.
ma'am, we thought you were in the introduction slide.
Oh, okay, okay. So sorry, so sorry. Okay, okay. I also didn't notice. Yeah. Anyway, I'll be sharing the slides with you. Yeah. So we were in the slide. Okay. Yeah. So yeah, we were talking about different types of memory. Yeah. So we talked about episodic memory, and then second is semantic memory. So semantic memory means like you might have um, learned you might have learned about AI, you might have learned about deep learning techniques, you might have learned about machine learning techniques, and now you're learning about agentic systems. So these are all the and you might also have some general information, like the capital of France is Paris, the capital of India is New Delhi, and all these details. So these are all facts or concepts that you have learned through your life. That is the semantic memory that you have, right? Now, what is procedural memory? So if you know how to cook a biryani, that's a procedural memory that you have. If you know how to drape a sari, that would be a procedural memory that you have, right? And that is so based on the information that we store in our memory. So you have different categories. So likewise, how do you provide these kind of information to agents? Okay, that is what we'll be looking into. Now, second category is like based on the scope of the memory. Like I asked you, right? I asked you what you had for breakfast today. You might be able to remember, but if I ask you like 100 days before what you had for breakfast, you may not be able to remember. So, but if I ask you like maybe like where did you study or in which school did you study, you may be able to remember, right? Yeah. So based on the scope of memory, you can classify it as short-term memory and long-term memory. Okay. So so in ChatGPT or Gemini, if you go, you will have these conversations, right? So you might have asked for one particular, you might have had discussions on one particular topic, and then you might have switched to another topic, you have started a new conversation, right? So each of these conversations that you see in Gemini or ChatGPT is what you call as a conversation thread, right? So each of these conversation is called as conversation thread. And if it has to remember, so I asked about like, give me some options for a holiday, like the summer. Okay. And then it might give you some options. Then I might ask like, okay, give me an itinerary for the vacation. So it might give, okay, if it gives an option, okay, I chose Thailand, and then, okay, it'll give me an itinerary for Thailand. Where do I visit? And then I ask so many follow-up questions. So it is able to give me the answer because it is able to remember what I asked before. So remembering what I have been asking through an entire conversation is what you call as short-term memory. But if I switch the conversation, if I start another thread, it may not be able to give me the answers related to the another thread. Okay, so all these threads will be independent. Now, but there are certain things that agents learn across the session. Like, for example, I might have given some information in one thread saying that I'm a lead AI engineer working in PixDynamics or something. It might have learned this information as a user detail, or I might say like I like Python code, I'd like to code in Python, so it might have learned my preference as Python code. So I might have given this information somewhere in any of the threads. So it will identify my personal preferences. It will identify my personal details. And whenever it is trying to give me responses, it will try to personalize that response for me. Okay. So maybe, so every time nowadays I get, okay, as a senior engineer, this is how you would design every time I get this in my conversation these days. So that's because it has learned my role. It has learned my preferences. So I always get a Python code, okay, whenever I ask for a code. So these are personal preferences, and that is what you call as a long-term memory. So that memory is there across whatever sessions or whatever conversations that I start. That memory is there across the different sessions, and that is what you call as long-term memory. So these are the two categorization we have for different types of memory. Okay. So before we go into how we implement all these things, I will just quickly brush up on on land graph, because we would be using land graph for the implementations. So I think yesterday's session, Alexis already gave you an introduction into land graph. So land graph, as the name suggests, okay, it works. You are defining all the workflows as graphs. Okay, you might have, I think all of you are from the academic background, so you might all be aware of graphs. So in graphs, there will be nodes and there will be edges. So that is how a graph is made. And this is how any workflow is defined. So you need to also understand that whenever we talk about agentic architectures, you're taking land graph. So land graph is only used for defining agents. No, if you want to define a simple workflow also, you can use. So it is just a platform to help you build workflows. It could be agentic workflows. It could be just workflows. Okay. So the different components, you need to understand the different components of how you are building a workflow in land graph. Okay. One is the most important part is the state. So as we already mentioned about the relevance of memory, like if the Yeah. So state means like if I have performed a particular step, okay, whatever computations I've done, whatever information I've gathered till that step, I need to save it somewhere, right? So I will be saving it in the state, okay. And when I do the next step, I will be passing this state to the next step, okay. Now each and every step you have to define each and every step, and each and every step is defined using a node. So every node in land graph represents the logic or step that you have to implement. So what does a node do? It will receive information from the previous node through the state. It will do some computation. It will update the state, whatever it has done, whatever computation it has done, whatever information it has got, it will update the state and pass it to the next node. Okay. Now, how does this node know where to fetch data from and where do you have to send the data? That is defined through edges. So functions that will determine which node to execute next, that will be decided by the edges. So every time you define a flow, you have to define the nodes, you have to define the edges, and you have to also give a definition for a state. That means what are the informations you need to store at every point in time for the particular flow to work. So you have to define the state, you have to define the nodes, and you have to also define the edges, the connections between the edges. Okay. So you will have a start node and you will have an end node. You will have all the other nodes and edges in between, right? So here you can see you can have a start node. So first you start, you go to the agent. The agent has a tool capability. Now in edges, there are two kinds of edges. Okay, you might have fixed transition or a straight edge, or you might have a conditional edge or a conditional branch, you can say. Okay. Conditional branch means based on the condition. So if you are defining an edge from one node to other node, this is like a straight edge or a fixed transition from this node to this node. But if there is an option that it can either use, suppose this agent might be given multiple tools, right? It might not always use the tool. Okay, if the agent does not want to use the tool, if it is not required, it will just go to end. If it has to use the tool, it will use the tool. So this is the condition. Based on the condition, so that is what you call as a conditional branch. So whenever you have this land graph diagram, whenever you see this land graph diagram, all these straight edges would represent fixed transitions. All the dotted lines would represent conditional branches or conditional edges. Okay. Okay. So in land graph, you have something called as a super step. It's like usually it is after a single node execution, but then nodes that are, sometimes you might have nodes that are running parallel. Okay, so nodes that are running parallel are part of the same super step. Okay, why I'm explaining what is super step, I need to refer to the, in a way I'm referring to memory. You might require this. That's why I'm just referring to this. What is a super step? Okay, so usually you can understand super step as one node execution. After one node execution, it's a super step. But if you have multiple nodes that are executing at the same time, all of these will be belonging to the same super step. So at the start of the graph, all the nodes would be inactive. Okay, so a node becomes active when it receives a new message. So message from a previous node. Okay, from any of the previous nodes, if it is receiving a state, if it's receiving a new message, then it becomes active. The active node will then run its function and will respond with the updates. At the end of each super step, the nodes with no incoming messages will be on halt, right? If there are no incoming, you will that node will be on halt, okay, or inactive, you can say. And full graph execution will terminate when all the nodes are inactive, okay, and no messages are in transit. That is how you execute the complete graph. Okay, so this is about basic. This is about the basic land graph idea. I hope you got the land graph idea. So if at all you have any confusions regarding land graph, you can just quickly raise any questions, simple questions if you have. So I just wanted to take a feedback now, like, are we going good? Are we, is the pace okay? Can we continue?
Yes, ma'am.
Yeah, if everything is good, then we will move into, we will see some code, okay. So first of all, let me, if you want to, so this is the first code that will be running, okay, simple graph. So you have the key session, you have a, you can see a secret key here, secret key symbol here, key symbol. So that is the way you can add your secret keys, okay. You can just click add new secret key and you can add your secret keys here. Okay, if you have created a Gemini key, you can create here, you can add here, okay, fine. Okay, so I have added my Gemini keys here. Okay, so for today, I will not be executing the collab files because you would run into Gemini quota issues. So I will just, I've already run the files, so I will just explain it from here. So first and foremost, we have to get whatever key that you have set, right? You have to get the key, right? So you have to set your Gemini API key. Okay, so this is how you get your Gemini API key. So I think,
Please share your screen.
sorry?
Your screen is not visible.
Not visible?
Yes, the screen is actually visible.
Okay.
It is visible as of now.
Okay, fine. Yeah, so you have to set your Gemini API key first. Okay, this is the first step. Okay, then you have to, as I mentioned, LangChain and LangGraph are the two frameworks that we would be using. So we will, first, second step would be to install these two packages. Okay, once that is done, we will quickly define. So we have discussed about land graph flow, right? We will just quickly go through how you define your graph workflow. Okay, simple workflow. Okay, suppose,
Ma'am, can
yeah,
I interrupt? Actually, the screen is not moving.
Or is it?
It is, yes, the screen is not moving. If you're scrolling down, it's not reflecting to our screen.
Just a second. Okay. So let me know if it's moving now. No?
Yes, ma'am.
Now you
Yes.
are presenting me.
Is it moving now? I mean, I'm scrolling down. Are you able to see the screen?
No, the scroll is not seen. Yes, right now it is.
You're able to see the scrolling down, that I'm scrolling down, right?
No, ma'am, it's not moving.
It's not moving.
Ma'am, scrolling is not visible. The screen is visible, but when you scroll down, it is not coming
Okay,
with
let me just check. Okay. So now are you able to see the scroll? I mean, see down?
Yes,
Yes,
ma'am.
ma'am. Yeah.
Yes, ma'am.
Yeah?
Yes, ma'am. Yes, ma'am.
Yeah. Okay, great.
Thank you, ma'am.
Yeah, okay. Yeah, so as I mentioned, first you have to set the Gemini API key, and then you have to install LangChain and LangGraph. Okay. And then we will look into how you are defining the flow. Okay. So we'll take a simple example. Okay. So so you have, so first we'll import typing from typedict. Okay. So if you're unaware of this, typedict is like a Python type hint. Okay. So it was introduced after Python 3.8. So you know that Python is a dynamically typed language, right? So you don't have, you like how you do define in C int A, int B, you don't do that in Python, right? You directly assign values. It will take any values. A equal to 1, it will take. A equal to Munia, it will take a string. It can take any values as in when it comes. It's not like in C. Okay, you don't have to define the type. But whenever you need to define something, where you are explicitly giving some values or some types, okay, consistent value types, if you want to maintain, you can use this capability. Okay, so you will first define, you will import typing, and then from typing you will import typedict, and you will define, and this is what you call as the state of the workflow. Okay, so you're defining the state of the workflow. And here the problem is you have an amount in US dollars and you are converting the amount into INR, Indian rupees. Okay, so basically it's like, I have some investment, okay, maybe in US dollars, okay, and then that investment gives me some return, okay, and then first I have to calculate what what is my return. So I have invested $10 and then I got some 8% interest. So $10 plus 8% interest, that is the total return that I will be getting. And then whatever amount I get, I have to convert to INR or Indian rupees. And this is the workflow that I'm trying to implement. Okay. So what are the informations that I have? At any point of time, I need to save the amount in USD. Then I have to calculate the total dollars or total return that I get. And then finally, I have to convert to INR. So these are the three values that I will be keeping in the workflow at any point in time. So this is my state, or this is my memory for now. Okay. So next, you have to define the nodes. Okay. So as I mentioned, you have to define the state, you have to define the nodes, and then you have to define the edges. Okay. So next comes the nodes. What are nodes? You are defining the step at every step, at each and every step, what you have to do. Okay. That is what is defined by the nodes. So what is the first step? You have to calculate the total, right? So from the state, so every node will take state as the input. So you can see there are two nodes here. One node will be for calculating the return, and the other node will be to convert that amount into INR. There will be two nodes. Each node will take state as the input. It will compute, so it will update the corresponding values. Okay, here you have taking the amount in US dollars, and then you are just considering it as 8% interest. You are multiplied by 8%, and you will update the total USD. Okay. Now what is the next step? So that will be your next node. Okay. You are updating the node. You are updating the value as what you are converting. Suppose the rate, US dollar rate is 85. Okay, it may not be correct, but I'm just taking some value, multiplied with the whatever conversion rate, and then you get the INR. So you have defined the state, you have defined the nodes. Okay. Now we are building the graph. Now you have to build the graph. Building the graph, the first step would be you have to initialize your graph. Okay. So in LandGraph, so every time you are building a graph, there are three things that you import from landgraph.graph. Okay. One is a state graph. State graph is the graph that you are initializing. And then, as I mentioned in the slide, you will have a start node and you will have an end node that is already defined in the LandGraph. Okay. So every time you define the graph, you will start from this node, and every time you are ending the graph, you will end with this node. Okay. So first you initialize the graph, then you add nodes to the graph. Okay. How many nodes are there? There are two nodes, right? One is the name of the node, calculate total. You give it here, and you also give it a name. So this is a string value that you can give any name. Okay. Calculate total node, or calculate total, or total node, or you can give any name. This is a string value, but this definition has to be exactly same as the function that you give here. Okay. So you have two nodes. You add the calculate total node, and you have the convert to INR node. These are the two node definitions. Okay. Now the next step, so you added nodes to the graph. You initialize the graph, you added nodes to the graph. Next step is you have to add the edges to the graph. How do you define the edges? Always, as I mentioned, when you add the edges, there are two parameters you give. What is the start node? The next is the end node. Okay. So always you start from the start node, right? And then from the start node, where do you have to go? First, you have to calculate the total. So then you give whatever name you have given here. It's not the function name. Okay. It's not the node function name. It is the name that you have given here. You give the name. And from this calculate total node, you have to go to convert to INR node. And once you convert to INR, you have to end. This is a simple workflow. Then you compile the graph. So you have defined the nodes. You have given definitions to the node. You have initialized the graph. You have added the nodes. You have added the edges. You have compiled the graph, and now you got the graph. This is your start node. This is your calculate total node. You convert to INR and you end. So this is how you define any workflow in LandGraph. Okay. So now you have a compiled graph. You can invoke only a compiled graph. So you have to first compile the graph, and then you invoke the graph by passing the value. So what is the input that is required? Amount USD. Suppose I pass 1000 as the amount USD. It will compute, the first node will compute this total USD, and the second node will compute the amount INR, and I get the result as amount in INR as this value. Okay. So this is a simple graph. Now we will look into,
Ma'am, I think there was a question in the chat. Are you able to see the workflow?
Yeah, it's okay.
You were able to see the complete workflow, right?
Actually, the screen was visible. I guess it was the last workflow she was mentioning too.
Okay. So the second screen is now visible, right? So I've shared the second screen. You can see me scrolling, right? Yeah. Okay, great. Yeah. So we have we've just seen how you define simple graphs. Okay. Now we'll see a case where you have conditional edges. Okay. So the steps are the same. The first two steps are the same. Okay. So to define conditional edges, right? To define conditional edges, we will make this problem a little more bigger. Okay. So suppose the problem is similar, but just a small twist. Okay. So you have an amount in US dollars. Okay. You have to calculate the return. And depending on my country, depending on the country that I am in, I might want to convert into Indian rupees or euros. Okay. So at every graph execution, I will give, if I want INR, it has to convert to INR. If I want EUR or euros, then it has to convert to EUR. So it's a small change. Okay. So that is, so now you have three nodes. Okay. One will be calculate total node, and the other one would be, the rest everything would be same. Okay. And then in the one would be calculate total node, one would be convert to INR, one would be convert to EUR. Okay. There will be three node definitions. Previously you had only two node definitions. And in the state there will be one additional value that is called as target currency. Okay. Target currency, it can either be INR or EUR, no other values. That is why you are defining it as literal. Okay. Literal will help you to choose only the values between these two. Okay, you cannot enter any other value into this. Okay, so these are the only changes. Instead of two node definitions, you will have three, and depending on the EUR rate, you will update the EUR the rate value. Rest everything remains the same. Now, when you have conditional edges, there is another thing that comes up that is called as a routing function. Okay, so you need to know, right, based on what you will route to different nodes. Okay, you have to decide. Okay, so this decision for this particular problem, this decision depends entirely on whether you are giving INR or EUR, the string INR or EUR, right? So this is, so that is why this routing function will return that particular target currency. So depending on the value of the target currency, your decision will change. So the routing function means the routing function will tell you based on what you have to make the decision to go to one node or the other. Okay. Now and how do you define a graph? So similar to previous case, first you have to initialize the graph. There are three nodes. You will add all the three nodes. Then you have to define the edges. So from start, you have to calculate the total node. So that is the same. The difference comes when it has to go from calculate node to conversion node. Okay. So first you give the calculate. This is the source node. Okay. Now you have to decide on the destination node. So the second parameter will be the router function. Okay. So here you have a router function, choose conversion. And then choose conversion can have multiple values, right? There are two values it can accept. One is INR, one is EUR. Now the third parameter you give to this conditional edge function is a dictionary with all the keys would be all possible values that it can take, and the values would be which node you have to go to if I get INR. If I get INR, I have to go to convert to INR node. If I'm choosing EUR, if I get EUR, I have to go to convert to EUR node. Okay, this is the conditional edge that I'm defining. Then once I reach convert to INR or convert to EUR, I have to go to end. I can also have like two definitions. Okay, like convert to INR to end and convert to EUR node to end. I can also have separate, or you can give it as a list. Okay, then I compile the graph, and this is how the graph will look like. So as I mentioned, you will have the start node, you have the calculate total node, and then there are, so you can see the dotted lines, right? You can either go to EUR or it can be an EUR. If it is EUR, it will go to EUR node. If it is INR, it will go to INR node. Okay, and irrespective of whether you are in EUR node or convert to INR node, finally you go to the end. Okay, this is how you define a conditional edge. So this is the two different kinds of invocation that the graph can take. If I give amount in USD as 1000 and target currency as INR, you will get the corresponding total value here. If I give the amount in USD here with the target currency UR, you will get the corresponding values here. Okay. So these are the two categories of edges you can have. Either you can have direct edges or you can have conditional edges. Okay. I hope it's clear till this much. Okay. Sure. So next would be reducers. We'll be discussing about reducers. Okay, so we so far we discussed about state, right? The state we have, whatever data that you want to keep, and you can keep it here, and then you can give the data type here, right? So what we will look into, why keeping data types like this for certain use cases can be complicated. Okay, and that is why reducers come into help. Okay, we will see one scenario. Suppose I have a state, there is only one value, it is an integer value, and I've named it as foo. Okay, and there are three nodes which is trying to update the this value, same value. And sorry, there are two nodes. There is one more node. Okay, sorry, there are three nodes. There are like the node 1, what it does, it will take the foo. Yeah, so node 1, node 2, and node 3 all are trying to do the same thing. Okay, first node 1 will add 1 to it. Okay, there is no issue till then. Okay, your node definition is like this. You go from start, you have go to node 1, and node 2 and node 3 are parallel nodes. So from node 1, you are defining an edge to node 2, and from node 1, you are defining an edge to node 3. And then from node 2 and node 3, you go to end. This is the definition. So these two become parallel nodes, and both these nodes are trying to update the same value. Okay, so when you run the graph, you might get an error like this. Okay, it can receive only one value per step. Okay, because it does not know how to update. So either to update this and then to update this, or then first update this and then update this. Okay, it goes into like increment. So you are trying to update the same thing and update the same variable at the same time. Okay, so node 2 and node 3 are running in parallel. So you're incrementing like the same shared key in both the places at the same time. Okay, you don't know which one to keep. So that's why you have something called as annotated. So it is also, you're also importing annotated from typing. Okay, so what does this annotated do? So this annotated Okay. Yeah. So this annotated, actually, I have given the definition in another. Okay. So I'll explain about annotated in detail, but annotated, actually, it's I've given in another collab file details about annotated class. There is a I'll be sharing that also. Yeah. So annotated is capability that allows you to define the. So this is, again, you are telling that it is an integer. For Python, this value is a list of integers. Okay. Now the function, the parameter that you add next, right? That is called as a reducer. So the reducer will tell how you have to. So the reducer will tell how you have to deal with this. Okay. And this reducer here, what you have defined is an add. So you are defining add as a reducer. Okay. So this reducer will tell how you have to manipulate this particular variable. Okay. Now, you are able to see, right? Or is it stuck?
Yes, ma'am. We are able
Okay.
to see.
Okay, fine. So here you have the similar definitions, like you have node 1, node 2, and node 3. So here in this you are defining, so you have the state, you are taking this variable, you are saying that whatever comes to this, you have to add it to it. Okay. So you take the last, so if you are not overwriting the previous information, rather you are actually appending to the previous information. Okay. So when it comes to overwriting, that is when the conflict comes, right? So the reducer will tell that don't overwrite. Okay. Whatever comes, you just append to it. Okay. So that will reduce that conflict between the updations. Okay. So in the node 2 and node 3, you are just adding the values. Okay. In the first node, you will have one addition, and in the second node, when you add, you are getting 1 plus 1 as 2, and in the third node, okay, you will get 2 plus 1 as 3. Okay. So in this case, see, initially you have 1, and then you have 2, and then all these nodes will update the values as 3. Okay. Since you are not updating the previous value as 1, 2, 3, and 4, there is no confusion because you are just adding into it. So initially, you are passing the value as 1, right? So initially it is a list. So initially you are passing the value as 1, right? So in the node 1, it gets updated to 2. So you are not updating the previous 1 to 2. You are adding 1, 2. Okay. And when it comes to node 2 and 3, it is working on the same 2. Okay. But it is not updating the same 2. When the node 1, the value is changed to 2, it is added to this value. And in the node 2 and 3, it is working on the same 2, but not updating to the same 2. So it will have three values added to it. So node 2 will add 1, 3, node 3 will add 1, 3, and you will have a list of messages. Okay. So if you are saying that you can only concatenate to the list. Okay. So this is about reducers. Okay. I will also explain in detail in the next use case. Okay, I think we're already close to 1 hour, so I'll just go to the next one. I'll be explaining reducer there also. Yeah. So yeah.
There's a question in the chat box, ma'am.
Yeah. Let me see.
If it is possible to make more than one node as an end node.
No, there's only one end node. Okay, end node is only one end node. One start node, one end node. You're saying like you can have multiple flows in that case, or yeah, if you have multiple ways in which the flow can go, yes, you can have multiple end nodes, yes. But usually, yes, you define one end node and one start node. So I think yeah, I have is my screen visible now?
Yeah, ma'am.
Okay. So I've explained annotated detail here. Yeah. So you have this is like a simple chatbot. Okay. So initially you will define your LLM. Okay. So I will be explaining the annotated concept here also. Yeah. So this is, you are defining your LLM. Okay. So here since we are using Gemini, we will define the LLM as your Gemini LLM. So first you initialize the LLM. So this is the Gemini would be the LLM you're using for the demo right now. And then you are defining. So in case of chatbots, so previously we discussed about an integer value. In chatbot, you would have a list of, so here also we will discuss the importance of annotated here. Okay. So in chat messages, right? You would be adding to the messages. Okay. This is because it's a chat conversation. Okay. Now you are defining, there is only one node, that is a chatbot node. Okay. And then you're building the graph, you initialize the graph, you add the chatbot node, and then you add the edges. So you will have a start node, you will have a chatbot node, and then from chatbot node you will end. Okay. And you compile the graph. Okay. And then if you ask, sorry, I've just I think, let me try to run this at least. Okay. So this is how you get the graph. Okay, you have the start. It's a simple chatbot. You start, you go to the chatbot node, and you end. Okay, there is nothing complex here. Now you are creating a message. So so this is how you are defining. So for the LLM to process, you have to define the role, and then you have to give a content, and then you define the message as a dictionary. Okay, you have the role, and then you have the content, and the content is your question, right? Now you have created the graph. Now you're invoking the graph with the message, and this message is given as a message list. Okay. Oh, sorry. Okay. One more attempt, I'll try. I'm sorry. Okay, I think it is run out. Yeah, this one. Okay. So when you are when you are invoking the LLM, okay. So the message you send would be like a human message, and the message you get back from the AI would be the AI message, right? So if you look at the response here, if you're printing the response messages, you are getting only the AI message, right? Who invented telephone? I asked, okay, and I got back the result as Alexander Graham Bell. Sorry, Alexander Graham Bell as most. So it gave details about Alexander Graham Bell, okay, but it did not give me any information about my question. So where did my question go? Okay. Now, but this is not the way you want a chatbot to work. You want your question to be there and then your answer to be there. You want your next question to be there and you want your next answer to be there. And that is how you want your memory to grow, right? So, so here you have defined, so like how you define foo as int, you have defined here message as a list of, as a list, right? List of messages, yeah. So instead of list, you are defining here as annotated. So here for annotated, in a detailed explanation of what is annotated class, okay. And then in the previous example, instead you were defining add, okay. In this example, you have a new reducer function for messages called as add messages. Hello.
Yes, ma'am. The screen is visible. Yes.
Okay.
Go
Yeah.
on, sorry.
So yeah. So here instead of, so here your type is list, okay, and your reducer function is add messages, okay. So this annotated, as I mentioned, is used to add some context. So this is how you define the annotated, like in general, okay. And T is the type. So for Python, when Python sees, it is a list. So for in the previous example, it was just an integer value, and here it is a list. For Python, it is a list. But why do you have all these metadata added? Okay, so for land graph, this metadata, this is the reducer function. Okay, so land graph, how land graph would see this is, okay, it will in land graph, this reducer function would tell that whatever messages that comes, right, you add to this. Okay, this is what is the purpose of reducer here. So you have, previously you had an add reducer, now you have an add message reducer. This is specifically for adding the messages. Okay. Now if you run this node and then you define a chat using a loop, you can have a conversation. So you are asking who invented maybe telephone. Okay, it might give you some answer. Okay, where is, okay, so okay, some question I would ask. Okay, so it would, where was he born, Alexander Graham Bell. So I can go on. Okay, so I have defined a while loop. Until you give quit or exit, you can continue chat. Okay, if I give quit, I can exit the chat. Okay, so that is because I have given, I am able to add more messages to it because I have defined it as annotated. Okay. Yeah. Next, we'll look into how do you add tools to it. Okay. Yeah. So that was a simple chatbot that you just ask questions and it gives you an answer. Okay. Now you need to also add in tools, right? Tools to the tool capabilities, additional tool capabilities. Okay. So again, I'm taking an example of stocks. Okay. So like I have different stocks. Okay. So again, you have a state. So since it's a chatbot, definitely you will have messages. Okay. I have defined as annotated. Okay, no worries on that. Now, every tool is defined using an add tool. Okay. And then if I give the definition, this is just a, usually stock price, how do you fetch the stock price? You would have an API, you would fetch the data. So for simplicity, for the demo purpose, I've just given a dictionary. Microsoft value is this, Apple value is this, Amazon value is this, and all those Reliance values is this. So I've just given some abbreviations and the corresponding sorry. Yeah. So yeah. So again, so this is the tool definition, and then first you have to get the list of all tools. Okay. So you have in LangChain, you have to import the tool. Okay. For the tool definition. And then you have the list of tools. So here you have only one tool. Okay. First you have to define the LLM, and then you have to bind those LLM. So that means you are binding those tools to the LLM. So that will tell the LLM that, okay, you have these capabilities with you. Whenever you want, you can use these tools. Okay. When you run this code, you will get an error. Okay. Because how does an LLM identify what tool it is and in what cases can I use this tool? Okay. So you need to define, so it will tell you that, okay, function must have a doc string if description not provided. Okay. So usually it is expecting some sort of a doc string here as an explanation of what that tool is. Okay. So the tool, every LLM understands what the tool is used for from this definition. Okay. So previously you are getting an error because you have not given any docstring value indicating why do you use this tool, for what purpose you have to use this tool. Then only the model will be able to understand that it has these capabilities and it can use these capabilities in these particular scenarios. Okay. So you define the tool, you list the tools, you define the LLM, you give the capability of the tools to the LLM, and then you define the graph. Okay, it's a similar way. You initialize the graph, you define the chatbot node, okay, and you define the tool node. You also need to define the tool node. Okay, you start, you go to the chatbot node, and from the chatbot node, you are giving a tool condition. Okay. The tool condition means you can either use a tool or not use the tool. Okay, and from the tool you are going back to the end. Okay, this is the initial definition. Start, you have the chatbot node, you have the tool node, and you're going to the end. Okay, you can either directly go to the end, or if you required, you can use the tool and you go to the end. Okay, now when you invoke the graph, so suppose I'm asking a question, say what is the price of Amazon stock right now? Okay, what it will do, the chatbot node will try to identify that, okay, I have a tool which has the capability I have defined here This returns the current price of a stock given the stock symbol, param symbol. Okay, so stock symbol and the parameter symbol is a stock symbol, and the return, you have to return the current price of the stock. So since the LLM knows that I have a tool with me which can return the stock price given a symbol, then and the question is what is the price of Amazon stock right now, I can use this tool. Okay, and that is how it is able to return 150 value. Okay, it will return the Amazon stock price. Okay, it will fetch this from the tool and return the value. Okay, now okay, I ask another question, I get the answer. Okay, now I say that I have another message, like I want to buy 20 Amazon stock using the current price. What will be the total cost? So initially I've asked for Amazon stocks price. Okay, and then what will be the total cost? Okay, what happens is that it will understand that I'm asking something about Amazon stocks. Okay, it already has a tool that can retrieve you the value of Amazon stocks. Okay, so it will go fetch the value 150. But ideally this question should actually give me the answer as 20 multiplied by 150, right? Why it is giving 150? Because you have defined the chatbot node. Chatbot realizes that I have a tool, it uses the tool and gets the result, and tool node is directly going to end. Okay, it got the information, but it is not able to, the tool has no capability to understand what to do with the 150 value. Only the chatbot is intelligent, chatbot node is intelligent enough to do what like to understand what you have to do with the value. So what you have to do is, whenever you have a tool node definition, you have to define an edge back to the chatbot node, so that once you get information from the tool, the chatbot has to decide what to do with the tool, right? So chatbot knows that it has a tool, it will use the tool, it will get the information. Now once the tool node has completed execution, only when it goes back to the chatbot node, it is able to make further decisions. Otherwise it will just return the value from the tool node. It cannot go further, because from the tool node you are directly going to the end. And that is how you define. Okay, let me just that is why you should always have, I'll just quickly go through this. That is why you should have a graph definition, that for after every tool usage, you should go to the chatbot node and you go to the end only from the chatbot. In this case, if I ask a questions, it is able to intelligently use the tool, see if I ask, I want to buy the same question here, in this graph definition, it is able to identify, fetch the $150 from the tool, and it is also able to analyze that the current price of the Amazon stock is 150. Therefore, the total cost for 20 stocks would be 150 multiplied by 20, and you get the value. This happens only because you have a definition back to the chatbot node. Okay. Okay, now let's quickly get back to the Yeah. So we got an idea about how you define the graph, how you define straight the nodes, the edges, the conditional edges, and what are the things you have to be careful when you are designing a chatbot node, and how do you add tools, and what factors you have to keep in mind when you have to add tools. So this is the basic understanding about how you are defining the workflow. And then, so far we have discussed about state, right? So that is one form of memory that you have, like what information has to be updated at any point of time. So, so we discussed about two kinds of memory, right? One is a short-term memory, and the other is a long-term memory. So short-term memory is something that is confined to a particular session, right? So in land graph, you can define this short-term memory in what is called as a checkpointers. Okay, so I had also discussed about superstep, right? Yeah, superstep. So that is why I had discussed about superstep previously. Okay, so how the short-term memory or memory corresponding to a particular session is handled in land graph is using checkpointers. Okay, so checkpoints means, so I said every conversation that you have is called as a particular conversation thread, right? But you call it as a thread. So checkpoint is the state of a thread at any particular point. That is what you call as a checkpoint. Okay, if you want to retrieve information about at any particular point, you have to refer the checkpoint value. So that will give you an object called as a state snapshot object. So this object will have all the information related to what all information that particular workflow has at any point in time. Okay. So this is the definition that will tell you which particular conversation that you have to, you might have, so as I showed, there will be multiple conversations, right? How will you know which conversation you are referring to? That is defined by the thread ID. So whenever you are referring to any particular conversation, you are referring to that conversation by that thread ID. Okay, so you differentiate each and every memory of each and every conversation using the thread ID. So whatever is accessible for thread ID 2 may not be accessible for thread ID 1. So this is how you define the conversations. Okay, so why I define the super step is that this checkpoint, okay, when you're executing the graph, after every super step, this checkpoint will be saved. Okay, so every sequential, if it is a sequential node, after each and every node execution, you will save the checkpoint. If it is parallel nodes, it means all these parallel nodes will be corresponding to one superstep. There will be one checkpoint for all the combined together for all the parallel nodes. So after each step, you are saving the checkpoints. And for every thread, you will have multiple checkpoints. So at any point of time, you take the state snapshot. You will know what are the values that are currently present or currently saved in that particular conversation. Okay. So yes, we will look into that right now. So yeah, so this is how you add in. Okay, so I have taken the same example, okay, previously that I've discussed, get stock price. Okay, that would be the example we'll be taking for this. Yes, the same, I have the definition. Yeah, I have the definition of the graph. Now, what is the change that you have? Okay, here I have defined something called as memory. Okay, this is the land graph capability. The memory saver is the land graph capability that is provided from this package, land graph checkpoint.memory. It has something called as a memory saver. Okay, that will help you to define threads and differentiate each thread, and you can also save conversations of a particular thread. Okay, so the only difference from the previous example or previous code is that you have defined a memory saver here, and rest everything is same. Rest everything is same except one thing that I defined previously, that is the config. This config will define the thread we are referring to or the conversation we are referring to. Okay, so every checkpoint belongs to a thread. Unless and until it does not get the thread information, it cannot be tracked, right? So the only difference is when you invoke the graph, you have to pass this configuration to say that this message belongs to this particular thread. Okay, that is the only difference. That is, you have to define the memory saver, you have to initialize the memory saver, and then you have to define the configuration, and you have to give that particular configuration when you are invoking the graph. Now here I'm asking, I want to buy 20 Amazon stock using the current price. Then you have to add, then I want 15 Microsoft, and then Microsoft stocks, then what will be the total cost? Okay. So here it is able to keep all these details in the memory saver. Okay, so it is able to compute the current price of the Amazon. It fetches. It is able to calculate how much is the price for 20 Amazon stocks. Again, it will fetch from the Microsoft stock. It will compute for Microsoft. Then it will compute the total cost. Okay. So all these informations are stored in the state. Now, how do you get this information? If you want to get the complete state, you can go for get state history. If you want to get the state of a particular instance or a particular step, you can go for get state. Otherwise, for a complete history, you can go for get state history. Okay. So get state history will have the complete set of all the values, throughout the execution. And but if you go for say get state, okay, it will have the state snapshot of a particular instance. Okay, there will be multiple state snapshot, or there will be multiple checkpoint for a particular thread, right? So if you want to get all these values, you can go for get state history. If you want to get only for a particular checkpoint, you can particular point, you can get for get state. Okay, and yes. Yeah, so if you look here, and if you look another scenario here, okay. So initially I asked for, say, Amazon price. I asked everything, all of these details in one single question. It was able to answer because we have given, after the tool usage, we have given the chatbot node. Back to the chatbot node, it will be able to make decisions. Okay, it is also asking for Microsoft. Okay, I will again use the tool. Again, I'll fetch, and I got the result, right? Now, using the same thread, so using the same configuration, I'm asking another question. Using the current price of RIL, tell me the price to buy 10 RIL stocks and add it to the previous total. When I'm saying previous total, okay, how do you get the previous total? From the previous conversation. Since I'm using the same thread, okay, I will use the same thread. Okay, Okay, it will have information in the short-term memory, in the memory saver, that I am referring to the previous total as this 6004.5, and then it is able to intelligently understand that and add it to that particular total and give me the result, right? Suppose I'm starting a new conversation. Okay, so I'm giving the configuration as thread ID 2. Now this thread ID or this conversation has no idea about what I discussed in the first conversation, right? Now I'm simply asking a question using the current price of Microsoft. Tell me the price to buy 10 MSFT stocks and add it to the previous total. Now it will give you an answer as I can get the current price of Microsoft, but I don't know what the previous total is. Could you please provide the previous total? We have already discussed about the previous total, but that was in a different thread. That was in a different conversation. So this conversation or thread ID 2 has no information about the thread ID 1. That is why it is giving you this message. So this is why this is how you have a clear separation between the different threads. Okay. Because when you are, when you are building chatbots in production environment, you don't want, I don't want my conversations to leak into your conversations, right? So I don't want whatever I'm asking, I don't want my conversations to get to you, and you don't want your conversations to get it to me. So it's in case if we are having multiple threads of conversations. Okay. So yes, now checkpoints. So we've already discussed about checkpoints and get state. Yeah, that's about different threads and different. Yes, that's about this get state and get state history. Okay, so so we have discussed about how to implement, say, short-term memory, and how do you save conversations of a single thread. How do you also separate multiple threads, right? So now, what if you want, like, so since this memory savers, whatever we have discussed, right? So that is residing in the RAM. Okay. So if you want to store everything into a database, okay, you also have the capability of adding, like it could be SQLite, or it could be Postgres. If you want to add any database, okay, it is very simple in LandGraph. You just have to connect to that, you have to import that particular. So if it's SQLite, it's very straightforward. That's why I took SQLite. So you have to just directly connect to that database, and instead of the memory saver, you just have to give that particular details here in the memory. So that is the only difference if you want to connect to any database rather than putting the details in the RAM, so that you are able to get the information irrespective of maybe application startups. Okay, so this is how you can bring persistence to the short-term memory. Okay, I think that's about the short-term memory. Okay, so yeah, I think my screen is visible, right? The slides are visible, right?
Yes, ma'am.
Sorry. So yeah, so far we have discussed about why do you require memory, and we have discussed about different types of memory, short-term memory, long-term memory. And short-term memory we have discussed on how do you implement short-term memory and how do you bring in persistence to the short-term memory. This is what we have gone so far. Okay, so sometimes when you are managing the conversations or memory, you can't indefinitely grow, right? So there is you need to put a limit to it, right? So you don't have indefinite memory. You need to manage the memory somehow, right? So there are different ways in which you can manage this memory. So you can have one option would be a sliding window approach, where you keep only the last 10 transactions or last 10 conversations and you ignore the rest of the conversations. The other approach would be when the conversation gets longer, you can give the conversation to the LLM and ask it to summarize it, so that you are not giving a long conversation. Instead of that, you are giving only a summary of it. So you are getting the context, at the same time you are reducing the tokens. Okay, you can also have some filtering options, like maybe sometimes for a particular conversation, you say maybe you are giving only the last two conversations. Okay, maybe last two conversations are enough for a particular use case. Then you can filter out, or you can trim the conversations based on the tokens. Okay, you trim the conversations only up to the maybe 100 tokens or 1000 tokens. Okay, so these are different options. I have given a collab file also. Maybe you can just run it and just try it out. There are different options in which you can do this. Okay, yeah, so I think we will, yeah. So this is the image that I showed earlier also. So we have discussed about how you can maintain different conversations thread, how you can maintain information throughout a particular thread, and how one thread is separated from the other thread, isolated from the other thread. Okay. Now we have also discussed about another type of memory called as a long-term memory, where you have to remember those things irrespective of the thread, or you have to remember the details beyond the sessions. Okay, like a personalization. Okay, so how do you bring in that kind of a memory and how can you use LangGraph to bring in such capability? Okay, so what do you mean by personalizations? So I have already discussed about, like suppose I am coding, I say that I prefer Python code, or I like to build my APIs using Fast API over other frameworks. Then whatever code details or codes that the agent is giving me, that would be more personalized for maybe Python or Fast API. Okay. And then past interactions. Suppose I say that, oh, I visited Thailand and all those details. Then maybe if I'm asking for a new travel destination, it might not give me Thailand, it might give me some other destination. And then behavioral patterns, right? So suppose I'm continuously asking for it to give me structured, I'm asking it to refine every document in a structured list, using bulleted points. There is a great chance that when I give any questions, that will give me structured output using bullet points. Okay, it will learn my behavioral patterns and give me personalized responses. Another thing that you can add to long-term memory is specialized facts or documentation, or you can say like organizational data. So you can this is something that you provide in addition to the conversations. Okay, it's like an external data source that you add in, or it could be some historical outcomes, like the agent has tried out so many things, it did not work initially for multiple iterations, so maybe next time it would try a different option. So that is what you call as a reflection. So these are the ways in which you can try to implement long-term memory in land graph. So the straightforward solution is like a land store, it's land graph store, and then you have mem0 and lang mem. So land graph, so the only difference being one is the storage layer that land graph provides you, where you define some ways in which, so you will define like in what situations you have to store information. Say and you will have to define like the criteria based on which you have to store information. You don't store whatever conversations comes in, you don't store that, right? You have to filter out what conversations are relevant for long-term memory. Does it actually talk something about my preference, or is it something random? So you define what needs to be stored. And when you are making any new request, okay, to my request, you also add these personal preferences. And then you tell the LLM that these are the personal preferences of Munia. You also add these personal preferences when you're making an answer. So my question plus my personal preferences will go to the LLM, and that is how the LLM is able to give me a personalized response. And that is what you do in line graph store, okay? mem0, it is much more, it is an intelligence layer that will automatically, you don't have to define, it will automatically find out or extract the entities or relationship from the conversations, and it tries to update, and you get back the, it tries to update, and you can use that as a personalization layer, okay? So we will just look into the code. Okay. So I hope I'll be able to keep up the time. Yeah. So yeah. So long-term memory. Yeah. So this is the land store, land graph store implementation. Okay. So the initial steps remains the same, and then this is how you are defining. So you import the relevant packages, and then this is how you define your lang store. Okay. So you have something called as in-memory store, and this is the capability that LandGraph provides for long-term memory. Okay, and then apart from for running this collab file, you might also require one more key. So it's a nomic embedding key. So sorry, I could not mention that initially. So why we are using embedding here is that suppose I want to know my preferences, right? Suppose I'm maybe asking about, say, any particular topic which is not, which you cannot retrieve it using a keyword-based search. Okay, like could be like, let me think of. So like like the same example you can take, like I want to go on a vacation and then suggest some places. Okay, so and whatever information, personalized information that the model has collected would be like top rated places or top rated travel destinations by this person. Okay, top rated travel destinations and vacation spots. So I'm asking for vacation spots. Okay, so these keywords does not match, right? But it is semantically same. I'm asking for vacation spots and whatever preferences top rated tourist destinations. That is the keyword wise it does not match, but semantically it matches. So we want to bring in some sort of a semantic understanding here, and that is why we are going for embeddings. Otherwise, simple keyword match would be fine, right? But here, simple keyword match would fail in most of the scenarios. So, so since we don't have a lot of time to explain embeddings, but I would just give an idea about embeddings. So embeddings are for every sentence. If you are converting that textual data into numbers, that would give you a vector representation. And this embeddings are created in such a way that very closely similar words or sentences would be close towards each other. They will have less distance between each other. Those are semantically similar will be close to each other. That are semantically different would be far away from each other. This is how the embedding models are created. Okay, so that whenever I have a sentence, I try to find a similar sentence. I will most probably get a very semantically similar sentence than something which is dissimilar in nature, not in regard to keyword, but in regard to semantic understanding. Okay, so since we need semantic understanding here, that is why we are going for embeddings and not a keyword match. Okay, and then this is how you define the store. So defining the store would require what sort of embeddings. There are different. Nomic embedding is one of the embedding models. There are different types of embedding models available. You can go for any embedding model. You have to define the dimension, and you have to define the field. Okay. So in memory store, so you have to initialize the store with an index config. This is the index config. Okay. Index, you are defining the embeddings, which embeddings you're using, you're defining the dimension, and you're defining the fields parameter. Fields parameter will tell the store exactly which parts of your stored object should be returned to the vector embeddings for semantic search. Okay, you can think of it like a suppose you have text like this. Okay, content is like I love spicy food. Okay, the source, the detail would be like a JSON. This is the JSON structure, key value pairs. Okay, so content is like I love spicy food. Source is like it came from the chat, and this is the timestamp. So I don't want to store that maybe source or maybe the timestamp. So that is not relevant. So for which sentence I want to create the embedding? I want to create the embedding for I love spicy food. So because that is what represents my preference, right? So the fields parameter represents that. And then, yes, this is a combination of short-term memory and long-term memory. So you have store as a long-term memory, and you have the memory saver as a short-term memory. Okay. This is a combination that we have used here. Okay, so we have the same example defined here. And then another concept that you have to understand is that when you are, as I mentioned that, you differentiate each and every conversation using a thread ID. You differentiate each and every user by their namespace. Okay, so so whenever you are defining the chatbot, okay, first you will identify the user. How will you identify the user? You will identify the user from the configuration. The user will have a user ID. So every conversation will have two things. One is a user ID, one is a thread ID. User ID will define the user, and that user ID will correspond to a particular namespace in the long-term memory. So every like chat that comes in, that chat comes with two identities. One is a user ID that will define who is sending this, and there will be a thread ID that will define which conversation that user is referring to. Every user ID will be mapped to one namespace. Okay. Now, you in the chatbot you have to define. So what you have this namespace. Okay, this is the user. You have the namespace. You pass the namespace. This is the store.search. You are searching for what personalized experiences or for this particular user. So you will have the you don't need the thread ID, right? You want that personalized experience for that user, not for that conversation. So you have the namespace. Then you have the last user message. Okay, you have taken the last user message. And then you want to pick the top 3 preferences. Why you don't want to pick all the preferences? You want to pick only the preferences. Suppose I'm asking for travel places. I don't want to get any preference related to I'm interested in Python code, I'm interested in Agentic AI. I don't want to get all those preferences. I want to get my preferences about travel destinations, nothing else. So that is why you have a semantic that is why you're passing your last user message. So whatever is very close to your last user message, those preferences will be returned to the past memories. And then you append these past memories to your actual query and get your personalized responses. Okay, this is the chatbot definition. You also have a reflection node. What does reflection node do? Reflection node will define what has to go into the long-term memory. Now the reflection node you are defining, so there are different ways. You can statically say that if the length of the maybe sentence is more than 10 words, you store it. That is also fine, but that does not make sense, right? So you give it to the LLM to understand that question and ask, okay, does it make sense? Like, do I have to save this? Okay, does it say anything about the user? You are saying that extract any permanent user preferences, facts or goals mentioned. If there is nothing important, return none. So only if there is, if does not return none, you will create a unique ID. You will store that memory ID into that namespace along with the content. Okay, so this is one. So this along like if this is relevant, if a particular conversation is relevant, you store it to that particular namespace using, and that will be given some memory ID. Okay, so the reflection node will define what has to be saved, and then chatbot node will have some functionalities related to searching the particular corresponding preferences related to your query and adding to the system instruction. Okay. And yeah, I think so. Yeah, I'll just quickly go through the how different scenarios work. Okay, so I've defined a function. Okay, that will you have a user, you have 2 threads. Okay, you have a user A and you have 2 threads. Okay, so this function will invoke the graph and give you the responses. Okay, you can go through that function. I'll just quickly get through different scenarios. Okay, so I asked what is the price of Microsoft. Okay, and this is the same user. Okay, user A is asking in first conversation what is the price of Microsoft. Okay, and then so you get the price of Microsoft is 200.3. That is correctly fetched. Okay, since we have long-term memory, okay, that is in store. Okay, we have defined a long-term memory. So it will try to identify whether it is something related to the preferences, and it will find that, okay, it is asking for Microsoft price, and if this person is interested in stocks, and it tries to save this price of Microsoft into the long-term memory. And then I ask the next question. Remember that I own 50 shares of it. 50 shares of it. Okay. And then you have something like, okay, I will remember that you own 50 shares of Microsoft. Okay. So here in this thread, the agent will remember what we just discussed within the same conversation thread. Okay. Because we are referring to the same thread, it is the same user, it is the same thread, it knows what it has asked before, and it is able to remember that I'm talking, when I say it, I'm referring to Microsoft. Okay, now it knows, now there are two things it knows, that Microsoft price is 200.3 and I have 50 shares of Microsoft. Okay, that user A, I am referring to user A. Okay, I'm user A, and then I have 50 shares of Microsoft and the value is 200.3. Now I have a different thread. Okay, it's the same user, it's the same user, but a different thread. Now I want to sell my holdings. What was the stock I mentioned earlier? Okay, in previously when we were talking about short-term memory, if I ask some question related to the first thread, thread 1, if I ask some question in thread 2, it will not know. Here, since it is the same user and we have saved the conversations related to the previous question into the long-term memory, even if I'm asking from a different thread, it is able to remember it. I want to sell my holding. What was the stock I mentioned earlier? You mentioned that you want 50 shares of Microsoft. Okay, so I get the response because it has saved my preferences that okay, I'm interested in Microsoft and I want to know the Microsoft and I have 50 shares of it and all that details. Because now here you're not using short-term memory, you're using long-term memory. Okay, I also discussed about the semantic understanding part of it, right? Even if you don't use the exact words also, you should be able to get. So calculate the value of my Microsoft position. So even if it should be able to retrieve that. Okay, I'm not saying MSFT and all that. Okay, but I'm giving a different semantically similar question also. It should be able to retrieve. Okay, so calculate the value of my Microsoft position. So you can see it says, okay, I can do that. You own 50 shares of Microsoft and the current price is this. So the value of your Microsoft holding is this. So it remembers all the things that I mentioned in thread 1, and it is able to answer it even if when I'm asking from thread 2, because it has saved it in the long-term memory. Okay, so I have also, since we are almost time, I have also prepared collab file for mem0. You can go through it. It is a more, you will be able to easily understand because once you have understood this concept, because it's more or less similar. It is more straightforward. You don't have to define the reflection. You don't have to define much. It intelligently takes care of what to save and how to retrieve. So that is more an intelligent way of doing it. And I think we can sum up things that we have discussed. Okay. So another thing that I wanted to mention was a RAG. Okay, so we have discussed about short-term and long-term memory, and then how do you add in semantic concepts, right? So RAG is a Retrieval-Augmented Generation. Okay, so if a user asks a question, it fetches the data from an external source. It adds this information and give it to the LLM and generate the responses. Okay. So every time you get some documents, it could be your organizational data. Okay, you know LLM has only fixed. LLM takes only fixed tokens. Like it has a window, right? Context window. So usually we split the documents into multiple pieces, and each piece is called as a chunk, and each chunk is converted to embeddings. So as I mentioned, the relevance of semantic understanding is very much important. That is why we are creating embeddings, and you store it into something called as a vector database. Vector database is a specialized database that is able to handle the semantic search. So that is why we are not using relational database. We are using vector database because vector databases are specifically designed for semantic search. So whenever a user query comes, it tries to identify the most similar chunks which is similar to the query. So it will be converted into embedding using the same embedding model. It will try to fetch the most relevant chunks, and this question plus the relevant chunks retrieved from it. Okay, and there will be a prompt. Okay, prompt. All these three together goes to the LLM to generate the response. So what is happening here, LLM is not confined to the things that it is trained on. It is also able to get some additional information from the external world in order to make so that it does not cook up new things. It is able to, yeah, it is able to actually give you more accurate results. Okay, because it is having your organizational data. If you're asking any questions related to your organization data, it might not have, right? So yesterday Alex was discussing about how do you update your scorecard or score details, right? There was a table that CSV file that you shared. So if you have some information like that regarding your personal, which is very specific to your organization, LLM might not know, right? So this is how you provide external knowledge to the LLM. Okay. So this is just, we have discussed all of these. Yeah, so you chunk the whatever data you get, you convert to embedding, store it into vector store. And then whenever you get a new query, you are searching from the chunks, you augment it with the prompt along with the chunks, and then you give it to the LLM to generate responses. So RAG helps you to give additional information or grounding. That is what you call as grounding, because it is not just answering from the data it knows. It is also able to ground the knowledge or confirm the knowledge from an external source. Okay, it is able to adapt to any particular specific use case. And also when you are having RAG, right, so you are taking only the relevant chunks. So if you have like 1,000-page documents, so you can also think of it like this, right? Why not I give the entire document for the LLM to scan and give the results? That is also possible, but that is technically not possible, because you give 10,000 documents or 10,000-page documents, it may not be able to process at once, right? When you are doing RAG, you are selectively retrieving only the relevant information that are semantically similar to a question and giving it to the LLM, thereby eliminating the context window problem. Okay, so you're focusing on the context you exactly want, so you don't get into the context window problem, plus you are getting accurate result because you are giving only that relevant context for the LLM to process. Yes, there are some advanced techniques which I don't think we have time to discuss. I think we'll just quickly summarize on what we have done, we have gone through so far. So why memory matters? Because memory is kind of a bridge, that will turn any stateless model into stateful agent. Okay, so LLMs are stateless. Through memory, you are giving the power to the agents to do multiple things and plan multiple things and reason, and by making it more stateful. Okay. Now we discussed about different types of memory. Short-term memory is like a post-it note. Whatever you want to remember for that time, you will just note it down in a post-it note, right? Episodic memory is some kind of a diary, like what you did, at what point of time. Okay, like in checkpointer, you say, right, at any point, what is the state of the graph? Semantic means it's like the encyclopedia, right? Whenever you want to know some facts, you refer the encyclopedia. So whenever the agent wants to know some additional information, it picks the information from external sources, which is called as a RAG. Procedural, it's a skill set that you have. You know how to wear a sari, it's a procedural skill that you have, right? You know how to drape a sari, or you know how to cook biryani, that's a procedural skill that you have, right? How do you give it to the LLM? You can give, you define the workflows, right? You have to calculate the total. You're defining the workflows, right? You have to calculate the total. Then you have to convert it into INR, and then you give the result. That is the workflow you're defining through the graph. Or you are defining through system prompts. Okay, you extract this information and then you add it to this. Then you take 20 more Microsoft stocks, and then you add it to this. And this is how you're defining the flow through the prompts. Okay, so this is how it gets a procedural understanding. Now, next we discussed about how memory is managed. Okay, so management is all about balancing recall with noise, right? Recall means what? How much are you able to remember? Noise means you have to forget what you don't have to remember, so that you are able to manage the memory. You have to remember what you have to remember, and you also have to forget what you have to forget. I think in life also. Yeah. So how do you add semantic memory? So that is how you that is what we finally discussed. RAG is the way you add semantic understanding or factual understanding or conceptual understanding to any LLM. So I think we can wrap it up here. Thank you so much for your patient listening.